Well, hi, everybody. In this video, I'm going to talk to you guys about how to solve linear differential equations. Now, linear differential equations can have any order. And in another video, I talk about the order of a differential equation and what the form of a linear nth order differential equation is. If the order is pretty high, even though it's linear and we kind of know its structure, it could still be pretty hard to solve. However, for first order linear differential equations, there's actually a really nice method. And I'm going to show you in the next few minutes how that method works and an example or two to illustrate it. The first thing I want to do is write down, remind you, if necessary, what is the form of a linear differential equation. And I'm going to just focus on first order. The form of this differential equation would be something like this. There would be some function of x times y prime plus some other function of x times y. And this would all be equal to, some right-hand side function of x, capital F of x. The a of x and the b of x, those are functions of x. Now, the first thing we're going to do is actually we're going to divide, in order to talk about this procedure, we're going to divide by the a of x to begin with, so that the y prime doesn't have anything associated with it. It's just got a 1 in front of it, basically. So I divide through by a of x. When I divide b of x by a of x, I will get some other function of x, which I'm going to change letters and call it p of x. All right. And similarly, on the right-hand side, when I divide, I'm dividing everything by a of x. Just going to take the whole equation and just divide through by a of x. It puts a 1 in front of the y prime, and it does change these coefficients. The big F divided by a of x, I'm going to call that q of x. So this is actually the way in which we're going to think about a first order linear differential equation. This is a good equation for you to learn and to try to remember. You want to recognize when a differential equation is linear. And it needs to be something where you can put it into this form right here. Now, when you look at this form, you realize that it's pretty specific. It has to fit a specific format. But for example, just to show you an example of one of these, if we had something like this, y prime plus 2xy equals 2x cubed, this would be linear. The p of x here would be the 2x, right? So in this example, the p of x would be 2x, and the q of x would just be 2x cubed. It's nice to identify the p and the q because we're going to need them in a minute when we talk about how to solve these equations. I wanted to mention, by the way, that this differential equation is actually not separable. One of the other very popular first order differential equations that students learn how to solve are separable differential equations. But in this case, if you actually tried to split the x's and y's apart, you can use some algebraic manipulation, maybe subtract the 2xy to the other side and do some factoring. Yeah, you can do that, but you're going to get stuck where you're not able to move all of the x's onto one side and all of the y's onto the other side. It just doesn't work. This differential equation, I'm just going to make this as a note, it's not separable. This is not separable. It's not separable. And so, luckily, it is in the form of a linear equation, and there's a nice method for how to solve a linear equation. And that's what I want to talk about. Once I've talked about it, I'll come back and maybe finish solving this example. But let's look at the general form that's in the box again for a moment. This is what I have in the box here. You see that there's two terms on the left side. And I've got a y in one of them here, and a y prime in the other one, and they're kind of two terms added together. Does it remind you of anything from calculus? It might. If you want to pause the video for a minute to think about this, if you like to kind of discover things yourself, this is a good time to do that. In a minute, I'll tell you what I'm thinking of, and it'll probably be much more obvious to you if you don't see it already. What you have on the left side are two terms where you've got the function y in one term and the derivative of that function in the other term. And then there's another p of x sitting here. But it looks similar to the product rule for derivatives. To me, it does. Do you remember the product rule? Let me just remind you over here. I'm pretty sure you guys would remember this. If you have two functions multiplied together and you want to take the derivative, well, you can take the first function times the derivative of the second plus the derivative of the first function times the second. And it really does seem like what you have on the left side over here is similar to that, because I see the y and the y prime and so on. Turns out it's not quite right. It doesn't quite work because I don't know how the p of x fits in with, the f and the g over here. But it's very close to being a legitimate product rule. So what we're going to do to actually create something on the left side that is the product rule is we're going to multiply this whole equation through by something called an integrating factor. So what I'm going to do is I'm going to draw a little arrow here. I'm going to multiply this through by what is called in the business an integrating factor I of x, which is to be determined. Now, it's important for you guys to realize I'm trying to derive all of this for you because I don't want to just give you the formula for how to do the first order linear differential equations. But at the end of the day, there is going to be a formula for I of x. We are going to determine it here in the next few minutes. And really, the only thing you're going to need to know is what that formula is. It's a formula you'll want to learn if you're serious about differential equations. So, but I am going to show you the whole derivation here. And I would like you to follow along, and hopefully this is going to make some sense to you. So what I'm going to do is I'm going to write it as I times y prime plus p of x times I times y equals q of x times I. So I'm just throwing this I all the way through the terms of the equation. And now for the left side to be a product rule, the result of a product rule derivative calculation, you can see I have the y prime here and the y right here. So then the p of xi should be the derivative of the I part. So we need, I'm going to write it this way, di dx, the derivative of I, to be p of x times I. You see, if that's true, if we have this, I prime is just p of x times I, well, then we have I times y prime plus I prime times y. That would be the product rule derivative of I with y. So this I that is to be determined, it's going to be determined by solving this. Look at what this is. This is actually a differential equation. Does it look like a type of differential equation that maybe we've learned how to solve at some point? It's actually separable. In a previous video, I talk about separable differential equations where you get all of the x's onto one side of the equation and you get all of the y's, or in this case, the i's, onto the other side of the equation. Guys, I can accomplish that, right? This is separable. Maybe I'll just come right here and show you. This is actually separable. I can put all of the i's on the left side by dividing the capital I underneath the left side. And then all of the x stuff goes on the other side. I pulled the dx up to the right-hand side. I have separated the big I from the x's. And I can now, if I remember how to solve separable differential equations, remember we just simply integrate both sides. When you integrate, di over I, you're simply going to get the ln of the absolute value of I. And on the right-hand side, I don't really know what to do with this because we don't know specifically what p of x is. That depends on the problem that we're looking at. So I'm just going to leave it as the integral of whatever p of x dx is. And now I'm going to solve for I, which I can do by exponentiating on both sides, right? When we did separable differential equations, this is something that we did regularly in some of those examples. So I'm going to exponentiate on both sides of this equation. On the left, I will just get absolute value of I by itself. And on the right, I will get the e raised to the integral of p of x dx. Now, remember that when we do these antiderivatives, there's really a plus c, right? But one thing I want to emphasize in this little mini talk right now, guys, is that we are only trying to find an acceptable integrating factor. This is not about coming up with the general solution for I. We don't need that. I just want one integrating factor that's going to do the job and turn the left side into a product rule for reasons that you'll see shortly, right? So I don't need to bother with the plus c. And in fact, I want to drop these absolute value bars, which costs me a plus and a minus, but I'm just going to grab the plus case of this. I don't need to look at both plus and minus. So what we are going to do is we are going to take the simplest thing we can that we know will work, which is to literally just drop the absolute value bars, drop the plus c, and call that our integrating factor. So this to be determined over here, we just determined it right here through the little bit of math on the right-hand side of my board. We have a separable differential equation for that integrating factor. And now we solve that separable differential equation and we actually find out what the formula is for that integrating factor. So this is one equation that you're going to want to know. You'll also want to know this one. This is the sort of the form of a linear differential equation. These two equations in the boxes here, those are key. Those are very important for us to know. What I want to point out now, though, is that if we have chosen our I in this manner, then our differential equation becomes, on the left side, it actually just becomes the derivative of I times y. Right? Of course, the right-hand side, we have q of x times I still. So just coming back to this previous line, the left side is just the derivative of the product of I with y. And we can now use this. In fact, this deserves to be something in a box as well. Very helpful to just kind of know this one. Because from here, it's actually pretty easy to solve for y. We just have to integrate both sides and then eventually divide by the big I. Okay, so now to solve for y, we integrate both sides of what we have in this box. Now, when you integrate both sides, you will get a plus c. And that plus c we will need to keep track of. Okay, so the plus c over here with the integrating factor, we can choose that to be 0 and not even think about it. But there will be a plus c on the step that I'm talking about here, where we're finally integrating both sides and then eventually divide both sides by I to isolate the y, right? So you are eventually going to have a plus c in your final answer. Guys, I have 3 boxes on my board here. These are the 3 things for the section on linear differential equations that you'll want to know. Okay, let's go and try that example that I was using earlier to start our conversation here. And let's see if we can solve it now using what we've just learned. Y prime plus 2xy equals 2x cubed. And what I would like to do is solve that. I would like to solve this differential equation. As we mentioned earlier, for the solution here, we've already gone through and identified p of x, which is 2x in this case, and q of x, which is 2x cubed in this case. We've done that already. So the next thing I'm going to do is, now that I know that it's a linear equation, I am actually going to write down what the integrating factor is. Okay, so the integrating factor is e to the integral of p of x dx. So I'll go ahead and put in the 2x right there for the p of x. And when I integrate 2x, I just get x squared. The integral of 2x dx is just x squared. Just one more time, reminding you here, we're not going to add a plus c on that integral because we're just trying to find an integrating factor that will work. And this one is perfectly good. Okay. Once I have that integrating factor, I can go straight to this box right here. And basically what I'm going to do is I'm going to write down the integrating factor times my unknown function, which is still y. The derivative of that is equal to q of x, which is the 2x cubed, times e to the x squared. Okay, so we have now used this integrating factor, e to the x squared, to turn the left side into a product rule. Finally, the last part of our process here to solve for y, we're going to integrate both sides of this. Okay, when I integrate the derivative of something, I end up basically canceling out the derivative, right? So I'm going to cancel out this derivative by doing the integration right here. So that means I'm going to get e to the x squared times y. And then on the other side of the equation, I will have to do this integral right here. This integral right here is actually best done with a u substitution as well. This is going to take a little bit of work, but this is not really the most important thing we're learning today. It's just a reminder about u substitution from calculus. The trick is to use x squared as u. And if I do that, then the derivative of that is just 2x dx. Okay, and so I'm going to go ahead and incorporate all of that stuff there into my next step here. I see that I have a 2, an x, and a dx. So all of that will become du, the 2, the x, and the dx. But there's actually 2 more x's here. This is x cubed. I've used one of them to be part of my du, but I have 2 more x's, and x squared can be changed to u. And then I also have e to the u. Okay, great. So that is a u substitution to get us to that point. And to do this integral now, the best way to do it, it's a standard example of integration by parts. So maybe I'll come up here and I'm just going to say, put a little arrow here. I'm not going to show all of my steps here. Integration by parts is certainly worth a little bit of review if you've never really mastered it, or if it's been a while and you want to review that. Integration by parts, the formula is just u e to the u minus e to the u. Okay, I will not show those details. If you need some extra help with that, feel free to go off on the side and work that out, or ask for some help outside. But the point is, this is the result. I am going to put my plus c on this one. And anytime you do a u substitution, you ultimately have to go back and replace everything in terms of the original variables again. So you'll see that my u equals x squared comes back into play again. So we started way over here with e to the x squared y. And now it's equal to that. The last step, what does it say here at the very end? Divide by I to isolate y. So I'm now going to divide by e to the x squared, and that's going to give me y. In fact, we can just write it like this if we want. I'll put the e to the x squared on the bottom and simply recopy this last expression directly above it. There we go. That is our general solution for y. Okay. There would be potential to sort of algebraically simplify this if you wanted, but it's not really necessary. Perfectly okay to leave an answer like this. Okay, so that is the process of integration by, solving a linear differential equation, excuse me. Maybe I'll just do one more example just to show you another one. If you're good and you don't need to see a second example, that's fine. You don't need to watch all of this. But for those of you who would like to see a second example, I'm happy to show you one. Let me come back up to the top here and let's just do one more example and then we'll wrap this up. So here's another example. Let us solve the following differential equation. Y prime equals sine of x times y secant of x minus 2. And the minus 2 is part of the parentheses there. And I'm going to restrict x here to be between 0 and pi over 2. Okay. Well, what I want to do is, first of all, recognize what kind of an equation it is. This is going to be one of the important parts of this. Is it separable? Would maybe be the first question we would ask. And we're going to find that because of this part in parentheses, we can't really separate the x's and the y's, right? Y and x are together right here with a minus 2 on the other side, and we kind of have to keep that whole parentheses expression together. We can't kind of pull it apart. It's not really separable. But what I will notice, for my solution here, what I will notice is that if I want, I could actually sort of multiply this out. The secant of x is just 1 over the cosine. So this is actually sine over cosine times y. Sine over cosine is tangent. So tangent of x times y, and then minus 2 sine of x. So this is just rewriting the expression a little bit. And I do want to rewrite it again so that it actually is in the correct form of a linear differential equation. So I'm going to move the tangent of x times y to the left side so that it fits the form of our differential equation. So remember the form? It's good to have this one in mind here. Y prime plus p of x times y equals q of x. So in this case, the p of x is actually negative the tangent of x. It is very important, guys, to keep that minus sign. See the negative? It's a negative, whereas up here it says plus. So because there's a minus here, that minus is actually part of the P of X, and we do want to keep track of that. And also we have Q of X, which is -2 times the sine of X. All right. Let's calculate our integrating factor. The integrating factor, that's the other second equation over here that we need to make sure we know. E to the integral of P of X dx. So in this case, we have E to the integral of minus the tangent of X dx. Okay. And this is the integration that we need to do. And I will save you a little aggravation on integrating negative the tangent of X. This is something you can do by U substitution, or you'll find this in any number of tables of integrals. I've got the minus that's from outside of my integral. And then when I integrate the tangent of X, I actually get the ln of the absolute value, in this case, of the secant of X. This is coming from a table of integrals. Now, I'm not going to put a plus C on this. Okay. And I'm going to use a little property of logarithms to move this minus sign as a power inside. So I want to cancel the E with the ln here, right? So I can do that if I move the -1 as an exponent. Well, if you take the secant of X to the -1 power, which is really just the reciprocal of the secant, you actually just get the cosine of X again. And because X is restricted between 0 and pi over 2, we actually don't need these absolute value bars on the cosine of X because it's going to be positive. Between 0 and pi over 2, it is going to be positive. All right, so here's our integrating factor, cosine of X. I have to remember the third thing then that we're going to do with that integrating factor. We're going to form a product rule on the left side. These are the three important equations, right? So on the left-hand side, I'm going to form, in this case, the product rule of the cosine of X with Y. And on the right-hand side, I take the Q of X. Q of X was -2 sine of X. And I multiply it by the integrating factor, which was the cosine of X. Now I'm going to integrate both sides. When I integrate on the left side, I just get rid of the derivative. And for the integral on the right-hand side, I think the easiest way to do it is to just do a U substitution. So this is just -2 times the integral of sine of X cosine of X dx. That's literally just U du, right? If I let sine of X be equal to U, the derivative of that is cosine of X dx. So this just becomes -2 times U squared over 2. Here I do need to remember my plus C. Okay, and we can clean that up by canceling the factors of 2 from the top and the bottom. Get negative sine squared of X plus C. And so we can solve for Y now by just dividing right here, right? I just need to solve for Y. I have to divide by the cosine of X. So I'll put that on the bottom. And then I just have to recopy what was upstairs in the numerator. And there you have what would be the general solution for Y. This is how to solve first order linear differential equations. They look like this. They require an integrating factor, which comes from this equation. And ultimately, you're going to express your differential equation using a simple expression with the product rule derivative of I times Y on the left side. So if you know these three equations, you'll be well equipped to handle solving linear first order differential equations. I hope that this is making some sense. I hope that you're enjoying the video and learning a lot from it. If you've got any questions for me, I want you to reach out. let me know what I can do to help. And in the meantime, keep working hard on this. And I look forward to talking to you guys again before too long. We'll see you again soon. Take care. Bye for now.